Let's expand on our discussion of superposition that we had in our videos on differential equations. So it'll help us as we look at these systems. What restrictions does superposition put on our systems, but how does it help us to be able to analyze systems, and how can we get around situations that superposition won't work? So the first point that we need to remember is that the principle of superposition holds or is true as long as the material and this could be a spring or even some medium, it just whatever we're looking at, is not stressed beyond their limits. So as long as they're not stressed beyond their limits, or you distort them in some way, then superposition will hold. The system will be linear. We're assuming linearity. Assuming the system is linear. And for complex waves or complex signals, we can decompose them into a series, an infinite series of sines and cosines. Or I'll say cosines and sines. And this is known as a Fourier series. Now, a little background on Mr. Fourier. He was a scientist who was studying heat transfers in materials. So he was looking at signals that were going into, or waves that were going into materials, and how they would heat based on the wave functions. And they knew how to solve the problems with single frequency waves. But when they started to put in more complex waves, the formulas that they had began to fail. They couldn't get things to add up correctly. And so Fourier was the one who figured out that if you could decompose these complex functions, these complex waves, into a series of cosines and sines, then you could take a certain number of them and do the analysis, and you just had to take as many as you needed, but he could add all the different responses from all the different single waves that he could then make up that complex wave, and he could understand how that that signal, a complex signal, would work based on all these easier functions to do. And we talked about this idea. in when we talked about differential equations. Fourier was the one who really pioneered this concept, and he wrote a paper about it, and he presented it. Well, he presented it to the committee at the time was Laplace, who was working on his own version similar to Fourier. Legendre, who was very large in the differential equation community, and also Legendre, who was also into differential equations. They were the heavies, so to speak. And they basically told Fourier that his presentation was weakly supported and not logically presented. And so he was never published in the journals that were of the day. And so he didn't get a lot of recognition for his work. But it's interesting that a lot of the technology that we use today, your iPad, your pad, your any pad that you have, tablet, anything that watches MPEG movies, listens to MP3 files, doesn't matter. That technology is based on the Fourier series. Even 4G, the telephone standard 4G, which is called LTE, and your Wi-Fi, uses a modulation scheme called orthogonal frequency modulation, and that is based on Fourier series also. So even though Fourier wasn't known in his time, he is known today because of his work. So we can take any signal, and we're going to use d function of x and t, and we can decompose it down to a formula This is going to look pretty complicated. And it does get a bit crazy. Now this is Fourier's form in two variables, two independent variables. Typically we do Fourier with one variable. It's a little bit easier. But there are formulas to be able to calculate these coefficients, a naught, a to the n, a sub n, b sub n. Not going to get into those. We'll probably talk about them a little bit more in chapter 16. But if I can come up with these coefficients based on this complex wave, I can reconstruct this signal based on these individual sines and cosines. In the case where you have two independent variables, the Fourier transform is actually a two-dimensional space, and well, actually a three-dimensional space. This would be your x-axis, this would be your t-axis, and this would be the magnitude or your function dxt, and well, let's say it's the Fourier transform. Let's put it a function, transform function here. So we'll call it the Fourier of dxt x comma t. And so as I go down this t-axis, at these points, I evaluate this direction in terms of t, and I make x constant. And x is going to be constant there, and I'll evaluate it in terms of t, third one here, and just keep going down the x-axis. And then for the t-axis, I'll evaluate in terms of x, and I'll keep t constant. So you create this 2 by 2 grid of Fourier transforms. Now you might think, well, why would I ever want to do this? Well, it turns out that your JPEG pictures are put together, making the individual pixels into a somewhat wave function. And then once it's in this Fourier transform, the reason why JPEG pictures can become so blocky is because they'll take out certain information from this transform. So they may delete this part, and by deleting this part they can save space, and that's how they get the compression, and it's called lossy compression. So just to give you an idea that Fourier transforms not only can work with complex waves, but it can work with different types of data to come up with some useful properties, things that we use today. Everybody uses JPEG pictures. And it's based off of this two-dimensional Fourier transform. Now, when does superposition break? Well, here I want to give you an example. I have a function here that I've put in. It's a square wave. And I've calculated the coefficients, and in this case I only need the a coefficients. I only need the cosine. The sine coefficients go away. And I've come up with a Fourier equation. I'm just looking at the first 25 terms. So what I get is the red line is my square wave, the thick red line, and the blue squiggly line is the Fourier transform. It's actually pretty close. And if the medium is linear, we can stay pretty close to the Fourier transform. But what happens when the medium isn't linear? And in this case, what I did is I put in the squared term into the cosine, and this could mimic some type of real-life material that has some kind of phase shift that's to the squared, and you get some kind of distortion. Looks nothing like the original wave. How would you overcome this? This is an actual real-life problem that was experienced back in the 1920s. I believe it was the 1920s, when they put in the transatlantic telephone line. The problem that they had was that the signal that would get to Europe was totally distorted, unusable. So the question was, how do you get it to the point where you can maintain the signal quality and yet be able to transmit the data across, whether it's the voice or data, whatever signal you have that you're trying to get to the other side. Well, here's how they came up with a solution. So let's say that you have your phone here. Sorry, I'm a bad drawer. And I'm going to send my signal across the ocean. So here, I'm going to use square waves because it's easiest to use. It's easy to see. So I'm sending my square wave, and what I do is I look and say, well, at this point, my square wave is doing something like this. It's getting kind of distorted. So what I'll do is I'll put a receiver here and a transmitter. So I'm going to put what's called an RX receiver transmitter. And the receiver transmitter is going to take and read the signal before it gets too badly out of shape, and it's going to then send it as a clean signal. And then as the signal goes down, it gets to another point and it gets really distorted. And I'll have another receiver transmitter, and it's going to clear up my signal. And I'll go down to another transmitter receiver. And another. Until I get to a point where I am at my other telephone. So it's these receiver transmitters at specific distances that clean the signal up and send a fresh signal down to the next one to overcome this dispersion. This is actually what they've done in the ocean. They actually put these receiver transmitters underwater. They would then take and put power on both sides, and they would provide energy for these receiver transmitters along that cable. And the distances, if I remember right, were about 10 kilometers. Now they've since updated and they're using light fiber optics. So fiber optics are a little bit better. It's about, I think, 100 kilometers in between these receiver transmitters. So this is how you would overcome a problem with dispersion. And it's a solution that works really well. Now you can tell how that they're actually doing this, because if you're talking to somebody across the ocean, you're going to hear delay. That is a byproduct of having all of these receiver transmitters. It puts in delay. So that's like you're talking and then the person talks like 3 seconds after, and your conversation's a little bit off because of the delay. It sounds a little bit funny, but it's a compromise. To keep the signal clean, you're going to have to deal with some delay. So superposition is very useful. It makes things a lot easier to analyze, makes problems a lot easier, and in cases where you have distortion, we tend to force superposition into the system by doing these kind of patches or corrections along the way so that we can maintain this use of superposition. So it's a very important principle, and it's a good thing to look at and understand how to overcome those kind of problems. You'll find it so much in engineering that it becomes almost classes in itself. You'll find different control classes and how to deal with interference and mitigating these kind of problems. You can spend semesters talking about this. So this just scratches the surface, but I hope it helps you to understand some of the principles of engineering and what you have to overcome in the future.